Seuss first described. And now that term is being used for any kind of carbon isotope change in the oceans or another reservoir like the land biosphere that is associated with anthropogenic change. Okay, so a funny twist on this is that he was probably a PhD, and so he was probably Dr. Seuss. That's a nice one. So this is a picture of, on the top, CO2 in the atmosphere. In the middle, it's the flux of CO2 in gigatons of carbon per year. Remember I told you that we're out at 7.8 now, but this was as of about 2000. And so the increase in fossil fuel emissions leads to an increase in atmospheric CO2. You haven't seen this before. This is a variation of the kind of isotope ratios that we use for stable isotopes. This is describing the radiocarbon composition of atmospheric CO2. So there's naturally radioactive CO2 in the atmosphere that comes because cosmic rays bombard the atmosphere, and they actually split nitrogen, I believe. Turi, is that right? This is where we get C14 in the atmosphere. So cosmic ray comes in, whacks a nitrogen atom, and we get radioactive CO2, and that makes its way into all the reservoirs that include carbon. So radioactive CO2 shows up in tree rings. That's where the data on the bottom come from. And this has been a useful indicator of the age of organic materials up until about the middle part of the 1900s. And then, in the middle part of the 1900s, we started blasting nuclear weapons in the atmosphere. And nuclear weapons testing in the atmosphere obliterated this natural signal. But this is the C14 Seuss effect as applied to tree rings. But the same thing shows up in DIC in the oceans. As you learned, maybe you didn't get the radiocarbon bit from Howie. But tritium in the oceans and C14 in the oceans have told us about how the oceans mix. And this bomb signal is making its way through all these reservoirs right now. This is what the radiocarbon composition of atmospheric CO2 looks like over the last, since just before the bomb testing really began. So this Seuss effect that I showed you on the last slide is this thing here. So there's a very, very small little dilution, but then we blasted all this radioactive CO2 into the atmosphere. So we doubled the natural amount of radioactive CO2 in the atmosphere in the early 60s. And then there was a big international agreement, a test ban in 1963, and we stopped doing this mostly, except for France and North Korea in the last while. So there's this slow decrease here of C14 in the atmosphere, and it looks like an exponential decay. What's the half-life of C14? Anybody know? Correct, yeah. So this is not radioactive decay because we haven't gone through 5,000 years at all, right? This is decades. So why is that going away? Atmospheric radiocarbon, the bomb signal in the atmosphere. Louder?
It's being taken up by...
It's going into the oceans and it's going into the biosphere. It's these net fluxes that I just described, okay? Dilution of this. So this is a really useful signal, and people make use of this in trying to understand things that have reservoirs with turnover times on a scale of decades. Okay, so soil carbon, for example, we can learn about the residence time of carbon within the soil system or within wood or things like that by watching for this signal. So this is it's not a natural signal, but it's out there and it's everywhere, including in your bones. And that signal is useful for understanding carbon exchange. So that's radiocarbon. The C13 composition of atmospheric CO2 is also changing. It's changing for the same reasons, but the fractionation factors that are involved are entirely different than radiocarbon. So on top, we see CO2, and this is reconstructed. This goes back to 1850 here. This is reconstructed from ice cores and from firn, which is snow that's on its way to turning into ice cores or ice. But it still exchanges a little bit with the atmosphere. And by looking at the C13 composition of those records, we can see that since the beginning of the Industrial Revolution or so, we've had a decrease in C13 of atmospheric CO2. Jim probably said it's -8 per mil. That's kind of the standard way that we teach it. It's really more like -8.23 or so, 8.2, 8.3 minus now. But it used to be less negative. Okay, why do you think it's going in the more negative direction? Fossil fuel burning. So why would fossil fuel burning do that? Fossil fuels are plants, right? Plants experience, C3 plants, go through a discrimination. So an atmosphere that used to be -6.4 turns into a plant that has a -6.4 plus or minus 18 per mil or so. And you get plant biomass that's more negative, just like a leaf. And then we store that, and it goes through geological processes. It turns into whatever fossil fuel we're talking about. Fossil fuels have a very negative carbon isotope ratio. Liquid fossil fuels have an isotope ratio that's around the high -20s. And gas fossil fuels have much more negative isotope ratios. So liquid, petroleum, LPG, propane, et cetera, these are methane, these are really negative. If you look at the isotopic composition of the emissions of CO2, this comes from economic records primarily, but from 1750 out to now, this has changed from about -24 to about -29, and this depends on the fuel mix. So an important feature, I've said that this is decreasing because of our emission of fossil fuels. If you were to make a mixing line that included that CO2 and that carbon isotope ratio of CO2 and try to back out a signature of what's being put into the atmosphere. Has anybody heard about a Keeling plot yet in this class? I'm going to give you the math for this at the end of this lecture. If you did a Keeling plot with this, you don't get a signature that matches the number that I just showed you on the other slide. It doesn't match, and it doesn't match because of something called the disequilibrium. Okay? So this reflects the entire carbon cycle that includes these one-way fluxes of photosynthesis and respiration on land that have different isotope ratios, and one-way fluxes of ocean uptake and release that have different isotope ratios. The fact that those are different is referred to as a disequilibrium, and it has important, very important implications for understanding the global carbon cycle. So we won't talk more about the ocean disequilibrium, but if we look at that change in atmospheric CO2 carbon isotope ratio that I just showed you, if plants haven't changed their discrimination over this time, and there's a discrimination here of, let's say, 18 per mil, then the photosynthetic products that are made from that atmosphere have changed their signature over time. Leaves are different now than they used to be because the atmosphere has changed. The source has changed. We're ignoring a discrimination change here. Now, if we keep some of that in the terrestrial biosphere for a few decades or up to centuries, then what comes out as respiration, decomposing organic material, reflects an older atmosphere because it's been stored for a while. And so the respiratory flux reflects a shifted back version of the same. And the contemporary respiration release flux and photosynthetic uptake flux differ in their isotope ratio. They're not in isotopic equilibrium, and this is referred to as the land disequilibrium. Yep.
Can we come back to the last slide?
Yep.
So what do you have the uptake in Delta 13C from 2000? Is that just do we sort of bring something different?
So you're wondering, why does it go in that direction?
Yeah, why does it go? Why does it
I don't know the answer, but this guy, Bob Andres, does. It has to do with the relative contribution of things that are being burned. It's going to be really different now because of the tremendous change since then in the US to the big switch to natural gas. Natural gas is going to be way more negative. And so these are not big isotopic changes compared to some of what we've been looking at. This is a few per mil, okay? But if you're burning natural gas that's like minus 45 or minus 50 per mil, a change in the proportion of natural gas versus coal can lead to these kind of wiggles. And there's also in there is this whole Soviet Union collapse signature. And so there are lots of papers that are devoted to this. I just don't know those details. Yep.
Can you go forward?
Yep.
Can you explain one more time the old versus new atmosphere thing?
Sure. So the atmosphere has changed. And it's changing from its old equilibrium system to adjusting to a new one where we are putting more negative CO2 into the atmosphere. And so it's going in a more negative direction. And because that atmosphere has changed, the products of photosynthesis have changed over the last few hundred years, simply because the source has changed. And that is where we get this photosynthetic, I mean, this is an arbitrary, this is a conceptual diagram, right? But that's where this photosynthetic signature comes from. And that reflects a constant isotope fractionation, which looks like it's 8, is that 18 per mil? Yeah, 18 per mil. So if that hasn't changed, then we would expect the products of photosynthesis now to be different than the products of photosynthesis 100 years ago. Respiration from the terrestrial biosphere is the decomposition of organic matter. So if a tree falls down and it takes 40 years for that tree to decompose, or if it takes 40 years for that to make its way through the soil system and come back out, then what's coming out reflects the atmosphere 40 years ago. And in a flux-weighted sort of sense, the respiratory signature is an older one than the photosynthetic signature. And so that's where this disequilibrium comes from. And there's an expectation here that the respiratory flux is more enriched than the photosynthetic flux. This comes from strictly assuming a constant disequilibrium and applying this kind of simple conceptual model. Make sense? Similar kind of thing with the ocean. Okay, the ocean uptake, the ocean release happen in different places in the ocean, and they reflect very different atmospheres. Think about what you learned from Howie about how things mix and how long it takes the conveyor belt to do its thing. The release of CO2 and the uptake of CO2 with the ocean are very, very different in their, not very different, they are subtly different in their isotopic composition. And so there is a thing called an ocean disequilibrium. And the fact that there are these two disequilibria is the reason that you can't do a Keeling plot with those data and get something that looks like minus 28 or so. It actually looks like minus 13 or so because of these signatures. Okay, so if you look at different ecosystems of the world and you look at the average photosynthetic discrimination of those ecosystems, that a generally accepted global average signature is something like 18 per mil. But it varies, and it especially varies if you have C4 plants, right? So C4 ecosystems here have much, much lower fractionation. These are values for that disequilibrium. Okay, small, less than a per mil, generally less than half a per mil for most ecosystems, and always of the same sign, meaning that respiration should be more enriched than photosynthesis. Okay, this is an old paper, 20 years old now, and this comes from the basic conceptual model that I just described to you. It's nearly impossible to measure this disequilibrium. I'll show you, though, that we've made an attempt to do that in a bit. Yep.
So right now, respiration is always more enriched than photosynthesis.
That's the assumption from this modeling.
Yeah, because there's the lifetime period.
Yep.
You just described, I guess.
Yep.
But in the past, as CO2 is kind of going like up and down, has that changed ever, or is that kind of standard for?
Well, I'll show you in just a sec. I'll show you a longer kind of timescale estimate of fluxes that are derived from all of this, and let's come back to that. So you got to pay attention to the distribution of C4 plants on the planet, and there are models out there that allow us to do this. When you do this and you come up with an estimate of what terrestrial discrimination looks like, it varies on the planet. It varies because moisture varies. C3 plants respond to moisture. It varies especially strongly because of the presence of C4. If you go back to those mass balance equations and you put in our best understanding of all of the signatures and you try to sort out the fluxes, this is the pattern of fluxes that we derive based on the global carbon, for the global carbon cycle. These have been smoothed to look at decadal patterns. Now on the left, the time scale is different here. So on the left, it goes from 1000 AD out to 2000. And you can see that the ocean flux and the terrestrial flux were basically zero. The net flux was basically zero because we had an equilibrium with the atmosphere. There was no change in CO2 during that time period. There was no change in C13 during that time period. Then we start to add negative CO2 to the atmosphere. We see it in the atmospheric signature, and we see the fluxes into the terrestrial biosphere and the oceans change. Okay? These systems are adjusting to the perturbation in the atmosphere.